When a Carnot heat engine is operated, with water vapor or steam as the working fluid, it is called a Carnot vapor cycle. We know that a Carnot cycle has 4 processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. We can draw this cycle on different graphs such as PV, TS, and HS diagram. By doing so, we can understand all of the property changes that are happening in this process. Since we're dealing with steam as the working fluid, we can draw the liquid vapor dome on all 3 graphs. Anything to the left of the dome is pure liquid. Anything to the right is pure steam. And anything underneath the dome is a mixture of liquid and gas phase. Our first process, 1 to 2, is isothermal expansion. We already know that phase change is isothermal. So in the TS diagram, we draw this as a straight horizontal line for constant temperature, starting from the saturated liquid line on the left to the saturated vapor line on the right. Next, in the PV diagram, there's something interesting happening. Usually, isothermal processes are drawn as a parabolic curve. But when the system is a mixture of 2 phases, such as liquid and gas, there is a special rule called Gibbs phase rule, which says that when the temperature is constant, pressure will also be constant. So we draw this as a straight horizontal line for constant pressure, from the saturated liquid line on the left to the saturated vapor line on the right. And for the HS diagram, we draw a curved line symbolizing constant pressure from point 1 to 2. The next process, 2 to 3, is adiabatic expansion. We know that reversible adiabatic processes are isentropic. So on the TS diagram, we draw a vertical straight line from 2 to 3, so that the specific entropy, S, is constant. On the PV diagram, for an adiabatic process, we draw a parabolic curve from 2 to 3. And for the HS diagram, we draw a vertical straight line for constant entropy from 2 to 3. Next, process 3 to 4 is isothermal compression. So in the TS diagram, we draw a horizontal straight line from point 3 to the point right below point 1. Because we already know that the next process needs to be isentropic. On the PV diagram, we draw a horizontal straight line from 3 to 4 for constant pressure, where point 4 has slightly more volume than point 1. And on the HS diagram, we draw a curved line, which follows the constant pressure line from 3 to 4, which is a point below 1. The last process, 4 to 1, is adiabatic compression. So we draw a vertical straight line on the TS and HS diagram, showing constant entropy, and a parabolic curve on the PV diagram. These are the graphs for the Carnot vapor cycle. For each of these 4 processes, there is a dedicated machine. For isothermal expansion from 1 to 2, we use a boiler, which provides heat input at a temperature of TH. For adiabatic expansion from 2 to 3, we use a turbine, which extracts work. For isothermal compression from 3 to 4, we use a condenser, which removes heat at a temperature of Tc. And for adiabatic compression from 4 to 1, we use a pump, or compressor, which takes in work. We can calculate the heat transfer from the equation, delta S is equal to Q by T, or Q is equal to T delta S, which is also the area under the TS diagram. Similarly, we can calculate the work done in adiabatic processes as the change in enthalpy H. So Q in is TH into S2 minus S1, and Q out is TC into S3 minus S4. Likewise, W turbine is H2 minus H3, and W pump is H1 minus H4. We know that thermal efficiency is desired output by the input given. Here, the desired output is to have some net work done, and the input given is heat from the boiler. But from the first law of thermodynamics, we know that for a cyclic process, the total heat transfer is equal to total work done. So the difference between heat input and heat rejected is equal to the net work done. We can use this in the equation for efficiency. Substituting the equations for heat transfer, we get the following equation. But since S3 is equal to S2, and S4 is equal to S1, we can take this common, which gives us the net work done, as TH minus TC into S2 minus S1, by TH into S2 minus S1. We can cancel out the entropy terms from the numerator and denominator, giving us the efficiency of a Carnot vapor cycle, as 1 minus Tc by Th, which is the same as that for a Carnot engine.